All right, next and last for our showcase today, we have Sid Gupta, who is mentored by Robert Alperon, who I believe is here. Would you like to introduce Sid?
Sure. Yeah. So my name is Robert. I'm at UCLA and I'm part of the NASA Center for Geospace Storms. It's one of the Drive Science centers. And this summer I had the wonderful privilege and pleasure working with Sid Gupta, who's a fantastically brilliant student in the sciences. And I believe he's about to start college at the Colorado School of Mines. So he's making a big move this summer. We worked with satellite data from the NASA FAST mission, and in particular, we're looking at particle data of um, plasma or particles from the Earth that escape into the magnetosphere. It's called ion outflow. So without any further ado, I'll leave it to Sid and go ahead.
All right, thanks. I will share my screen. There we go. Okay. This is our official presentation for the project we did this year. So in 1998, NASA launched a satellite called the Fast Auroral Snapshot Explorer, or FAST, into Earth's polar orbit. And its goal was to study how Earth's upper atmosphere interacts with the sun to cause space weather. And it also had an instrument on it named TEAMS. And so one of the things it studied was ion outflow, which happens in the ionosphere. The ionosphere is basically a layer of gas particles that gets ionized by radiation from the sun, like ultraviolet rays, X-rays, and these ions can interact with radio waves, broadband, extremely low frequency radio waves. And when that happens in the atmosphere, and when that happens at high altitudes, they can be given enough velocity to escape the atmosphere completely. This is what's called ion outflow. This is one of the things that's studied. And typically the ions that end up escaping are oxygen plus and hydrogen plus ions. So FAST observes particles in the atmosphere near the polar regions where the magnetic field is nearly vertical, longitudinal. And as particles get energized by BBELF waves, they leave the atmosphere, they do so in the sort of helical motion. And so the angle at which the ion in this, as you can see in this picture, the angle at which the ion is moving in comparison to the magnetic field line is called the pitch angle. So that would be this angle alpha right here. So a pitch angle of 0 degrees would mean it goes straight up and out. 180 degrees would mean it goes downwards, and 360 degrees would be back up again. So our goals for this project were to, number one, create a program, I use Python, that searches a large data set of observations and creates basically a catalog of specific events. And our second, more broader goal was to gain some insight into the physics of ion outflow. What exactly causes it to happen? And also to establish a foundation for future research. The program we made uses a database, a NASA database called OmniWeb, which has a bunch of different satellites, many of its past missions that measure solar wind conditions. And so OmniWeb gives access to something called the SIM-H value. And the SIM-H is basically an index for measuring how disturbed a magnetic field gets, magnetic field disturbance. So by providing it with a link to recalibrated level 2 FAST TEAMS data, the program basically downloads a file with that data, looks at it, and cross-references it with another database, NASA's official FAST TEAMS database. And so this is a flowchart for how my program works. I'm not going to go into too much detail, but basically what it does is it searches the OmniWeb data for times where the SIM-H value is over a certain number. And then it downloads all the data files for that time, and it makes a graph of them. And one of the limitations of my program is that it only works when you're taking a year's worth of data at a time. But this takes basically multiple numbers per second. So a year's worth of data is actually quite a lot. And so these are our graphs. This is what our data actually looks like. These are our sample events. On the vertical axis over here, you have PA, which is pitch angle. And the warmer colors on the spectrogram means more ions are at that angle. So these distributions specifically are called ion conics. And they're typically centered around 90 to 120 or 270 to 220 degrees. And because those are the angles where it has a vertical component of velocity and it can actually escape. So our first sample event has a SIM-H value of negative 143 nanoteslas. That's pretty big, meaning it happened during a storm, during a solar storm, but it also appeared when the Earth's magnetic field was in line with the sun, because the magnetic local time was about 16. And so magnetic local time is basically the direction of Earth's magnetic field in relation to the sun. Magnetic local time of 12 means they're exactly in line. So a magnetic local time of between 10 and 16 means they're like pretty close to connecting. And that region is called the cusp region. So this conic appeared during a storm in the middle of the cusp. And so our second sample event had a SIM-H value of negative 12 nanoteslas. So it didn't really happen during a storm. It happened during a quiet time, but the magnetic local time is exactly 12. So it happened in the cusp region, just like the first one. By the way, we use matplotlib in our Python program to make these spectrograms. And so our third sample event had a SIM-H value of negative 150 nanoteslas with a magnetic local time of 3. This distribution doesn't really look like a conic. It looks more isotropic, like all the colors are the same. There are the same number of angles at each, there are the same number of ions at each angle, and it also doesn't have a hydrogen plus component. So it happened during a storm, but it was out of the cusp near midnight. And so our last sample event had a SIM-H value of negative 150 nanoteslas, so it did happen during a storm with a magnetic local time of 17. This is a low altitude conic for both O plus and H plus, and it was taken during a storm, but at the edge of the cusp. So the results of our project were we constructed a program that easily searches and scans both databases, the OmniWeb and FastTeams databases, and archives specific events. And this code can basically be a foundation for future research of correlations between magnetic local time, geomagnetic activity, and ion conics. So we could do a statistical study with lots and lots of sample events instead of just 4. And so one of the days which we took a sample event was also simulated by a MAGE, which is a simulation model, a multi-scale atmosphere geospace environment model, which is developed by the NASA Center for Geospace Storms, or CGS. So this video over here shows the magnetic field during a solar storm on the left and pressure on in the magnetosphere on the right. And so these are our references. And yeah, that's all. Unfortunately, I don't have a thank you slide, but I'd like to thank this opportunity, NASA and N3 and Sonoma State University for providing me with this opportunity, and also for my mentor, for Dr. Alder, for helping me through this and getting to give me this opportunity.
Thank you. Thanks, Sid. Let's give a round of applause for Sid's awesome presentation. Very cool slide design you had there. That was interesting and fun. All right.
So Sid, do you think you're going to keep working on this project for longer now that you got the program running?
I might not be, I might be able to, but I also am starting college in like 2 weeks. So I might not be able to, unfortunately. I just hope that, I think this program will definitely make things a lot easier for people who want to study this, because now they can, instead of going and doing each thing manually and looking for specific sample events, now they can just do it for all of them.
Well, that's certainly the trend in research these days. People don't write reports about 1 or 2 events anymore. They like to have big collections of events or objects. So it's definitely quite the modern trend in research to have bigger and bigger data sets and collections of things.
Does anyone else have a question for Sid before we
So that was really great work. And we're so thrilled because Sid was one of our scholars and
Thank you.
come to all the meetings and ask a lot of questions, and we've always enjoyed working with you. So we hope to see you, coming to our future science meetings. All of the interns that are quote graduating today. We hope to see you in the future because we're going to continue with our monthly N3 science meetings. And so you'll always be invited, and I'll keep sending you opportunities and other things like that as they come along. And also, we will be hoping that you will tell your friends about the program so they'll apply in the future as well.